Audible?
Yes, you are audible, ma'am.
Okay. Now I would like to introduce our next distinguished speaker, Dr. Himdeep Walia. Dr. Himdeep Walia has been working in higher education domain for almost 2 decades now. Currently, she is working in TCS as subject matter expert and domain consultant, learning programs, higher education, having end-to-end ownership of learning products in the AI/ML domain. In her current role, she is working with INIs and universities to create degree program in domain like AI/ML, AR/VR, IoT, cybersecurity, and cloud computing with upcoming industry relevant courses to help stakeholders leverage the courses in a graded manner. Being an SME helps to directly connect with students to understand the learning gaps and other pain points and propose strategies to improve user experience and engagement. Her role also gives her the opportunity to interact with the stakeholders to gather constructive feedback on project development and enhancement. She has done her BTech and MTech in computer science and engineering, and her doctorate is in natural language processing, and her work is on word sense disambiguation for Punjabi language using intelligent techniques. Her research interests include artificial intelligence, machine learning, NLP, conversational experiences, and vision intelligence. She has filed 2 patents and has published research papers and reputed journals and international conferences. She is also a member of Computer Society of India, IEEE, and ACM. Ma'am, please.
Good evening, ma'am. I hope I'm audible.
Yes, ma'am.
Do I need to switch on my camera? Or is this okay?
Is it okay, ma'am? No problem.
Okay. So first of all, a very good evening to all of you. Thank you so much for joining in on a Tuesday evening. And I hope wherever you all are, please keep yourself warm. Okay. So I would like to thank the college for me for this session on advanced neural network architecture for generative AI. We are going to predominantly dive into the different neural network architectures which are there and understand that how this progression has actually led forward, why we moved from one neural network to another, and understanding that we are primarily focusing towards generative AI, what led to this whole journey. So I went a little overboard in thinking about what all different networks we need to talk about. So there are 10, and I understand the time limitation, but I'll try my best to ensure that we cover everything in a quite comprehensive manner. So we, catching little glimpse of the previous session which was going on, I'm confident about the fact that some of this has already been in the previous session. I'll just touch upon them and then dive deeper into the transformer GAN autoencoder architecture, and then even touch upon graph neural networks, spiking neural networks, capsule networks, and then deep reinforcement learning networks, which are the upcoming ones and quite popular in terms of its implementation with respect to different applications across different industries. Okay, so first question is that why are we even using neural networks? I mean, weren't we happy with supervised and unsupervised learning algorithms? So why we had to take up this? So let's take an example. So we have a bunch of people with us and we need to identify that whether, who is a boy and who's a girl. So please pardon me for being very stereotype here, but it's just experimentation that we are classifying that if any person admits that like gaming, we are going to classify them as a boy. And if any person admits that they like shopping, we are going to classify them as a girl. Having said that, we know that there are going to be two variables that we are going to use in order to find this classification. Basis on this, we should be able to identify, and there will be, asking these questions, and there is a percentage involved. It's possible that a person might say that they like 20%, interest in gaming, and they have 60 or 70% interest in shopping, thereby concluding that, this person might be a girl. But there is one issue which comes here, and that is the inductive bias phenomenon, which is more related to a psychological phenomenon which is there. Now, the machine learning models are primarily built with the assumption that if you have two variables, x and y, they're going to be related to each other. As an inductive bias of let's say a linear regression model, there will be a linear relationship between these two variables. So in that way, we are saying that, a line or a hyperplane might get fitted into this data that we have. Now, when this x and y variable a complex relationship, then it will get difficult for a model, let's say linear regression, to predict the value of y. Now for this situation, instead of going for a single line differentiation, we might be requiring some sort of a curve that takes into account multidimensional or some sort of an approximation to that relationship. And that's exactly the reason why we are making use of neural networks. Now, having discussed that, let's move on to the first one that we have, which is the feed-forward neural network. Now, this is considered to be one of the first adaptation of artificial neural networks that we have. And one significant feature of the feed-forward neural network is that it does not form any loops. This type of neural network is also known as your multi-layer neural network, as all the information that this network captures, it only passes it forward. What happens is that during your data flow, the input nodes is going to receive data, which is going to travel through the hidden layers, and then it will exit through the output nodes. As such, there's going to be no link that is going to exist in the network that can get used by sending information back from the output node. So if I have to really simplify this network, I can actually use it as a single layer perceptron also, wherein this model will actually multiply the inputs with respect to the weights that you are assigning to it as they are entering into the layer. And afterwards, this weighted input values can get added together to get a sum. And as long as the sum of the values rises above a certain threshold, which is normally set at 0, the output value can be 1 in case it is above the threshold, and in case it is below the threshold, it can be -1. So as a feed network, the single layer perceptron often gets used for classification, and the machine learning can also get integrated into perceptrons, and through training we can adjust the weights based on the priority with respect to the different inputs that we are assigning to, and therefore we can get the intended results that we are looking for. Now, there are certain components of feed-forward neural networks that are of primary importance, and we are just going to, say them out loud here so that when we are using them with respect to other networks, we understand what's the definition of each of these words that we are using. The first one being the input layer. Now, the neurons of this layer, they receive the input and they pass it on to the other layers of the network. And incidentally, these are the number of features or attributes with respect to the data set that we are using. So the advantage here that straight away comes with respect to any supervised learning algorithm is the amount of inputs that we can actually tackle when we are using a neural network as compared to other supervised learning or unsupervised learning algorithms there, where we have to limit them. Here we can go and take as many inputs provided we are assigning the required weights to them based on the priority. The next layer that we have is the output layer. Now, according to the type of model that is getting built, this layer is going to represent what is the output or what is the forecasted feature of your model. And then, of course, we have the hidden layers. Now, your input and your output layers are actually getting separated by these hidden layers. And again, depending on the type of model that you're going to use, there can be one to many hidden layers sandwiched between the input and the output layer. Now, every hidden layer is going to have a lot of neurons, and these neurons are going to transform the input before they actually transfer it to the next hidden layer. So this means that the network gets constantly updated with weights in order to make it easier to predict the final outcome. Then certain important terminologies that we use quite regularly with a neural network is a neuron weight. Now, neurons get connected by a weight which actually measures their strength or magnitude. This is, in a way similar to how a linear regression coefficients work. And normally this weight is between 0 and 1. Next, we have neurons. So the neurons actually work in two ways. First, they create a weighted input sums, and second, they are used to activate the sums to make them normal. Now, these activation functions can either be linear or non-linear. And there are different varieties of activation functions also. So we have sigmoid, where the input values are between 0 and 1, that get mapped to the output values. Then you have tanh, where the value is between -1 and 1, and this one gets actually mapped with the input values. And then the third most popular activation function that we have is the ReLU, or the rectified linear unit, where only positive values are allowed to flow through. And in case there is a negative value, it automatically gets mapped to 0. So we are covering the almost all the terminology that we usually associate with the neural network here. So moving on to the next one, we have the convolution neural network. Now this is one most significant development that we had with respect to neural networks. Why? Because when we moved in this direction, the primary reason was that apart from the data or the numbers in binary, we wanted to experiment more in terms of the inputs that we were working with. So we moved towards images, we moved towards audio, video signals, and in order to ensure that we are able to comprehend this type of inputs as well, we want a more sophisticated neural network. And this is where the birth of convolution neural network happened. Now, the major USP of this particular neural network is the type of layers that have been introduced over here. And every layer has been very thought after. And there's a specific reason that this layer is added and they have the desired functionality attached to it. So the first layer that we have is a convolution layer that you can see over here. And so you might have one convolution layer, or you might have more than one, followed by pooling layers. And then the final layer that we have is the fully connected layer. Now, each layer, your CNN increases its complexity that's given. Then it helps us in identifying in greater depth whatever input we are providing. So when I'm talking in terms of a CNN, I'm primarily stressing about the fact that the input will be more of an image or an audio or a video signal. So because of these layers that have been added, it ensures that we are able to uniquely identify each and every aspect of the input that is being given. So let's begin with the convolution layer and that what is the functionality of this one. So this is the code building block of your CNN, and this is where the majority of the computation will actually occur. So this layer itself is going to require a few components. For instance, it will require an input data, of course. It will require a filter, and it will also require a feature map. Let's take into consideration this input that we have. So this is a matrix of pixels which is in 3D. So this means that the input will have 3 dimensions with respect to height, width, and depth. So which basically corresponds to your RGB image. So now we also have a feature detector, also known as a kernel that you can see, or we also call it as a filter, which will move across the respective fields of the image and checking if the given feature is present or not. And this exactly is known as the convolution. Now, the feature detector is actually a 2-dimensional array which represents part of the image. Now, while the feature detector might vary in size, typically, so in this example, it's 5 by 5, but by default, it's usually 3 by 3 that we take into consideration with respect to the input. Now the filter is then applied to an area of the image, and a dot product is calculated between the input pixels and the filter. So for example, in this case, my input is 28 by 28 by 1 and my kernel is 5 by 5. Now the entire image is going to be covered by this filter, and we are going to calculate the dot product as we move forward. The final output from this series of dot products from your input and the filter is known as the feature map, or you will call it as an activation map, or in some cases, or in some research papers, we also call it as convolved feature. So, right, so now the weights in the feature detector, which remains fixed as it moves across the image, is also, at times we also call it as the parameter sharing. So some parameters like weight values, they can be adjusted during the training, so that and we do that, that updation usually happens by making use of back propagation or by making use of gradient descent. So primarily there are 3 hyperparameters that affect the volume size of the output. You have the number of filters that are being used. You have the stride, that is the distance or the number of pixels that the kernel moves as over the input matrix. And thirdly, zero padding, which is usually used when the filters do not fit the input image. Then we move on to the next layer, which is known as the pooling layer. Now the pooling layer primarily conducts dimensionality reduction, which means that it reduces the number of parameters in the input. Remember, I said was that the advantage of neural networks is that we can actually use a lot many attributes, frankly, all the attributes which my data set has as an input. But having said so, and after having moved from my input layer to my convolution, realizing that of all the given inputs, there are certain which hold more weight as compared to the other ones, we are able to actually divide them into such categories depending on which inputs are going to matter more in terms of finding us the correct output. And this exactly is what your pooling layer is supposed to be doing. So similar to the convolution layer, the pooling function sweeps a filter across the entire input, but there is a catch here. The difference is that this filter will not have any weights. What it will do, it will apply an aggregation function to the values within the respective field, thereby populating the output array. And then again, there are different types of pooling. So as the screen in front of you, what you see is a max pooling, and the other one that we use is average pooling. Now, what does a max pooling does? As the filter moves across the input, it's going to select the pixel with the maximum value to send to the average, output array. And with respect to average pooling, what as the name tells, it's going to calculate the average value with the respective field and send it to the output array. And then finally, we have the fully connected layer. Now, the name itself tells that what exactly is done here. So the pixel values of the input image that we have received, they are not directly connected to the output layer in this case, right? But the fully connected layer, each node in the output layer is going to be connected directly to the node in the previous layer. Now this layer is going to perform the task of classification based on the features extracted through the previous layers, and there are different filters. So while your convolution and your pooling layers are going to make use of activation functions, let's say ReLU, your fully connected layer usually is going to leverage a softmax activation function in order to classify the inputs, primarily with the probability that would lie between 0 to 1. Okay, so moving on to the next one, we have the recurrent neural networks. Now, this neural network is part of the deep neural network, which is basically trained on your sequential or time series data. Now, time series is one of the most important area of problem statements that we have, primarily because a lot of the problems that we are working or dealing with is based on a real-time series of events which is happening, and there is some correlation between what is happening now, what happened before, and what is predicted to happen in the future. And a lot of applications which we have even in industry, a lot of the products that we are building in industry primarily is dependent on the time series data. So again, the algorithms that we had been using were not quite significantly helpful in predicting the results as close to the actuality as we would have expected it to be. Therefore, the requirement of a newer model that would be able to comprehend this. And the reason with our supervised learning was the limitation of the inputs that we could take. Using neural network, we were able to eliminate that limitation, and therefore it has worked wonders in terms of sequential or time series data. Now, how is it able to do that? I'm sorry, please excuse my coughing. So what happens in your recurrent neural network is that we have a special entity that has been included in this network, and we are calling it as memory. Now, this memory is going to take information from the prior inputs in order to influence the current input that we are working with, and of course the output that we'll be finally getting into. Now, what was happening is that with your traditional deep learning networks, they assume that your inputs and your outputs are independent of each other. Now, the output of your recurrent neural network actually depends on the prior elements, which is within the sequence. So, your future events would be determined using the previous inputs which is there with respect to your unidirectional recurrent neural network. So let's take an example. For instance, let's say I have an idiom that says I have butterflies in my stomach. Okay. Now, in order to get the right meaning of this idiom, I have to ensure that the specific order in which the words are being said, the neural network is able to capture that. So, which means that your RNN needs to account for the position of every word in the idiom and then use that information in order to predict what is going to be the next word in the sequence. So each word in the phrase, for example, I have butterflies in my stomach, is actually a part of a sequence where the order is going to make a lot of difference. Now, the RNN tracks the context by maintaining a hidden state at each step. There will be a feedback loop that is going to be created by passing this hidden state from one time step to the next. Your hidden state is going to act as that memory that we spoke about earlier, which is going to store the information from the previous input. Now, at each time, your RNN processes the current input. So, for example, the word in the sentence that you have, along with the hidden state from the previous time. And this is going to help your neural network to remember what was the previous data point and then use that information to influence the current output. Now, there are different variants of your recurrent neural networks as well, but the one which is most popular and we will be using when we are going to discuss the other architectures as well is the LSTM, or known as the long short-term memory. Now, this particular neural network was basically introduced to overcome the vanishing gradient problem. And if I can pronounce the name correctly, the people who introduced this network were Sepp Ostreiter, and I think the other guy's name was Jürgen. I don't remember his last name, but these were the people who had created this network, and this work primarily addressed the problem of long-term dependencies. Now, let's take an example. Let's say I have the sentence, Alice is allergic to nuts. She can't eat peanut butter. Now, in order to predict what exactly is the preference with respect to peanut butter in the context of nut allergy, it means that in case Alice eats peanut butter, which has nuts, she is going to be facing some medical emergency, right? Now, how can we correlate these two sentences in order to ensure that when I'm using the word, the first sentence and the second, the system needs to know that peanut butter actually contains nuts. And this might be an information that might be in a previous paragraph on a previous page, or right in the start, and this piece is somewhere in the middle. Now, how these two are going to be connected? This is when the cells or that memory is going to make its usage of. So your LSTM networks are going to have cells in your hidden layer, and these cells are going to have three types of gates. One is going to be an input gate, the other is going to be an output gate, and then we have a forget gate. Now, these gates are going to control the flow of the information into and out of your network in order to predict what is going to be the output. And this is how we'll be able to correlate this sentence with the previous information that was already captured in these cells. Okay. So now we move on to the transformers and attention mechanisms. So the journey that we have taken has been quite eventful. As I mentioned, every algorithm was being used. So happy with supervised learning, but then we realized that there were limitations in terms of the inputs that we were making use of, in terms of the type of inputs that we were requiring in order to handle more and more diverse and complex problems. And that's when we started understanding that there might be certain more type of problems that again, these sophisticated neural networks are also not capable of handling. And in order to understand that, we move forward to understand that what next can be done. In order to do that, let's take, for instance, that you have a piece of paper with text on it and you want to build a model that can translate this text to another language. Now, how do you approach this? So basically, I'm talking about translation here, right? So the first problem is actually the variable size of the text. So apparently we are not going to have any linear algebra model that can deal with vectors that might have, varied dimensions. So what leaves us next? Frankly, the default way of dealing with such problems is to use the bag of words model. Okay. So what happens in this model? The data will be a vector of a massive number and as big as the number of the words in a language. And most of the vector elements will be zeros, as most of the terms are not going to be used in the text, right? Now, to minimize the size of the vector for computation, we will have to store the positions of the presented words which are there. Now, there is one important drawback or a problem with respect to your bag of words model is that it ignores the ordering of words. So, for example, if I have this phrase work to live, it is actually different from the phrase live to work. But the problem with bag of words model is that it does not keep in mind the ordering of the word. So the complete meaning or the context is going to change because of that. Now, in order to handle that, which means that in order to ensure that my data is kept in order, what we'll do, we can increase the dimension of the graph. So my n-gram graph can be converted into or can capture information such that it keeps into consideration that what was before it, that is n minus 1 gram, and then what was after it, that is n plus 1 gram. Now, in order to overcome that, we will have to increase the n, and this is going to increase the computation complexity in a huge way. So what do we have till this point? We have a text which is of variable length. Then this massive size of data that we are working with after applying the bag of words model. And in order to compute it, we are increasing the dimensionality of this data, which means that we need to use a new model in order to capture this complexity. And we thought of RNN and said that why not use this in order to tackle this problem. Okay. Now your RNN is actually similar to your n-gram model, but there is one difference, and that is the output of the current input is going to depend on the output of the previous computations. So the RNN will have its internal state, which is going to work as a memory, and it will be suitable for applications that are primarily with respect to your NLP or your speech recognition. So if we look at a typical RNN architecture, and particularly this diagram that we have on our screen, shows that the input at time t plus 6 depends on the hidden state of each previous step, and of course on the current input as well. Now it allows the network to keep a history of the previously learned parameters, that's there, and it also uses it to predict the next output, which overcomes the problem of the word order that we had. And it removes obviously the computation cost as well, as we are going to pass the words individually on our models. So we are able to tackle two problems by doing that, which means that this model is perfect, but in reality, it also has some issues. The first issue that we have is the vanishing or the exploding gradient problem. Second, we cannot parallelize the computation, which means we have to take it one word at a time. So this means that I need to take up another model that can overcome these drawbacks as well. So this is where my LSTM comes into picture. So the LSTM unit is divided into cells as we just discussed, and each cell takes three inputs. You have your current input, hidden state, and then the memory state of the previous step. And these inputs go through three gates, like we just discussed: input gate, forget gate, and output gate. So now what happens is that these gates that you have, they regulate the data to and from the cell. The forget gate decides when to remember and actually when to skip the input from the previous hidden states. And this is actually one of the most important gates that we have in the LSTM. And the advantage of this forget gate is that it actually helps us to overcome the vanishing and the exploding gradient problem. Okay, so using LSTM, we were able to overcome the vanishing and the exploding gradient in the RNN, but there are still problems inherited from the RNN model, which is we still have no parallelization. We still have the sequential path for the data, and which we have actually even more complicated. And then of course we have a problem with the hardware, again, because if I have to do it more, I'm combining my machines, which means that hardware integration is also required. And all in all, it means that I need another algorithm to overcome this problem as well. Okay, so just to form the the basis or the background, the problem that we were working we have not been able to address so far is the fact that a variable length problem on the sequence to sequence translation. This is the problem that we have not been able to address. In order to fix this problem, in 2017, a model was introduced that depends on attention mechanism. Now, instead of processing your tokens separately, what we do is that we divide our text into segments and then we try to learn the dependencies between them. This particular model is actually based on another architecture that consists of two components. The input is first passed through an encoder. The encoder will take a variable length input and convert it into a hidden state with a fixed length. Then the hidden state will go through a second component, which we call it as decoder, that converts the fixed length state to an output of variable length. And therefore, we call this architecture as the encoder-decoder architecture. Now, in your transformers, the input tokens are converted into vectors, and then we add some positional information, or we even call it positional encoding, to take the order of the tokens into account during the current processing of the model. The transformers are actually modified in order to make it resistant to any previous problems that we have been discussing when we were moving through the bag of model, CNN, RNN, LSTM. And then using stacked self-attenuation and fully connected layers for both the encoder as well as the decoder part of the architecture. Now, your encoder is actually composed of a stack of multiple identical layers, such that each layer contains two sublayers. You have your multi-headed self-attention mechanism that is followed by the residual connections, and then you have a simple wise fully connected feed-forward network. Whereas the decoder consists of a stack of multiple layers as such, and the first three sublayers, in which the first two layers are the same as the one your encoder has. And then we have a third layer, which is actually a multi-head attention over the output of the encoder stack. Now, this particular model was actually inspired by the human vision system. Now, as a brain receives a massive input of information from the eyes, and actually more than what a brain can process at a time, you are capable of seeing and not seeing a lot of things, and the brain categorizing that, what the focus has to be. For example, all of us are sitting in our respective rooms in front of our system, and I'm sure there's some sort of an activity which is going on around us, assuming that most of us are going to be at home, and at this hour all the family members are back, and you might see some movement which is there. In spite of this, your brain knows where to position your eyes frequently between this computer screen and whatever activity is going on beyond this computer screen. So taking a cue from this, we have developed these transformers. We can apply this methodology to the problem that we are working with. If we know the parts that can affect our translation, we can focus on only those parts and ignore all the other useless information that we might have. So when you are reading this article, you are paying attention to this article and you're actually ignoring the rest of the world. So this comes, of course, with the cost, and that cost is at times described as the opportunity cost. Now, we can select from different type of attention mechanisms like attention pooling and fully connected layers. So in attention pooling, the inputs to the attention system can actually be divided into different types. So you have your keys, which is your non-violational cues. Then you have your queries, which are basically your violational cues. And then you have the values, which is the sensory inputs that we have. Now, on the image which is there, I know it's not very clear, but basically we are trying to visualize the weights between the keys, that is the sensory, the non-violational cues, and the queries, which is the violational cues. Now the values in the keys are the encoder's hidden states, and the query is actually the output of the previous decoder. So this is how this is working. Now another important aspect of this is the scaled dot product attention. So this is more efficient in order to calculate your scoring function. And we are again making use of the three values that we were speaking of. So this calculates the dot product over the input query Q and the keys K with the same vector length, which is D. Now, when we scale them, we make sure that the variance remains with different vector lengths, and then of course we have to apply some sort of a activation, and we make use of the softmax function to get the weights on the values. One important aspect that we have is the self-attention. So primarily there are two important components that a transformer has. One is self-attention and the other one is the positional encoding. So the self-attention is a mechanism where the queries, keys and values are all from the same source. So which means that the self-attention, or some research papers also refer to it as the intra-attention, it is going to be faster than the recurrent layers with the sequence length, which is primarily smaller than the representation dimensionality. Also, this is used to learn the correlation of different words to a single sentence to compute representation of the same sentence. So, for example, when he had a food poisoning and he stumbled to death, or he's not living anymore, right? So these are the different words or phrases that actually represent the same meaning. So self-attention is able to capture that essence and inform that we are referring to same meaning, although using different phrases in the different sentences. The other important key component that we have is the positional encoding. Now, as the model has no recurrence and there is no convolution, so we are making use of we are adding a new layer in order to make use of the sequence order. Remember, we said that we cannot compromise with respect to that. So at the end of your encoder and the decoder stacks, the information is injected that contains the information about the relative position of the token in the sequence. This ensures that we are not compromising on the context of the meaning of that sentence, paragraph, essay, whatever. So work to live or live to work, if one of that is being used, the context has to remain same throughout the length and breadth of the article. Okay, so next that we have is the recurrence mechanism. The input of each layer is going to be concatenated in the following way. So the output of the previous layer, which is going to be the same as in the vanilla transformer or the basic transformer, and your, so if you can see in the image below, these are the gray arrows, and the previously processed hidden layer that is represented by the green arrows is going to be the extended context. Now, these are some of the popular variants of the transformers that we have there. The first one is BERT, and I'm sure every one of us who's part of this session is aware of this application. BERT stands for bidirectional encoder representations from transformers, and it was the one that introduced us to generative AI as such. So this was introduced by Google, and it actually performs very well in terms of the context of the word. So incidentally, my PhD was actually based on context. So what I had worked, so this was before large learning models came, and my work was more on MATLAB, wherein I worked on an algorithm that helped to understand or differentiate easily the context of a word with reference to the sentence that is being used. To give a very simple example, let's say the word is bank. So it can be a financial institution and it can be a river bank. So in what context are we talking about? And that meaning is captured from the other sentences which were prior to this particular sentence. So BERT is capable of gripping the exact context of the word within that sentence. So some of the key features that it has is that it has bidirectional understanding, so which means that it can consider both the preceding and the following words in order to capture the uh, ambiguity and ensure that, you know, from ambiguous we come to non-ambiguous. Next feature is the masked language model. So it can randomly mask words in the sentence during training in order to predict how well or how close it is to the actual. And then next sentence prediction. So this is where we are trying to predict that after this statement, what is going to be the next statement. This actually gave birth to GenAI. And some of the applications as text classification, NER. So if you are an NLP enthusiast, name entity recognition is something that you are already familiar with. And of course, question answering. And Google has made best of it by seeing tremendous how their search engine has improved. Okay, the bank was located by the river. Now, imagine the example that I had just given talked about bank. Now, how am I supposed to understand that what exactly bank refers here? Is it the financial institution or the river bank? Normally, the older algorithms would have made it a mess and they would have tagged it as a river bank. But the BERT understands that bank in this sentence actually refers to the financial institution. The next transformer variant that we have is GPT, that stands for Generative Pre-trained Transformer. This is developed by OpenAI, so this is something we don't need any introduction to. Understanding that I guess everybody is using now ChatGPT for everything. I saw a colleague of mine actually using it to print resignation letter. So we are making use of it in interesting ways. So it has some of the key features. For example, you have autoregressive modeling that predicts the next token with respect to the sequence which is going on. And then you have large scale pre-training. So this is the best part, that based on what all is there, it understands and tries to write or produce text that has no similarity with respect to the one with respect to the text that we already have. And then the fact that we are also able to fine tune it. I can give command that, you know, explain, let's say, transformers to me as a preschooler or as a PhD scholar. You know, it can do that for me in a matter of time. So some of the important applications: text generation, you're using it to craft essays, stories, or dialogues. We are using it as chatbots. And then, of course, the reason everybody is fearing is that we are using it for code generation, and Google has already told how much ChatGPT it is using, or generative AI models it is using to write code now. So, for example, if I give a prompt that write a poem about the ocean, I might get the output like the one you see on the screen. So I can become a poetess. The third one that we have is, sorry for my lame jokes, kindly excuse. Just trying to ensure that we all are awake. Okay. So the next that we have is T5, that stands for text to text transfer transformer. All the T's. So this is again developed by Google, and it is designed to handle tasks like translation, summarization, classification. So Google has been pioneer in terms of translation, and somebody who was working in NLP since my MTech days. So way back in 2012-13 onwards. So I've seen how much work has come a long way in terms of translation and the number of variants that we have captured and how nicely it's translating, and even ensuring that the grammar of the language in which it is getting translated to is also well adhered to. And this becomes quite a problem because there are a lot of languages in which the subject and predicate is differently placed as compared to your English language. So, for example, it treats input and outputs as a string of text regardless of the task. For example, translate English to French, the cat is on the mat. I cannot pronounce French, so, well, I'm hoping that this is what it says. And then, of course, ability and pre-training on diverse data. We are again using it for summarization, translation, of course, and then sentence completion. So summarize, I have a sentence that is the quick brown fox jumps over the lazy dog, and it is going to give me the output as fox jumps over dog. So this is the translation. This is a comparison between the three. With respect to the objective, BERT is primarily for understanding NLP task, GPT is for generating new text, and then your T5 is primarily for text-to-text framework. Then BERT and T5 is bidirectional, which means that we can go both ways. That's not the case for GPT. And then we have different applications with respect to core task and training task. Okay, so moving on to the next one, which is generative adversarial networks. Now, the best part, or the best thing that I like about GAN is that it is highly inspired by the concept of game theory. So anybody who has been loving AI since their engineering days must have gone through a lot of text covering game theory. And this particular algorithm takes inspiration from there, and it provides a very powerful framework in order to make use of it. So this was invented by Goodfellow in 2014, and with the invention of GANs, generative models actually started showing promising results in order to generate more realistic images. We have seen a lot of development or a lot of usage of GANs with respect to computer vision. And then we are also seeing a lot of resulting outputs in terms of audio and text as well. Some of the popular GAN formulations are your cycle GAN that transforms an image from one domain to another. And you have text to image, wherein from a textual description, you're able to generate an image. And then we have progressive GAN, where we are able to generate a very high resolution images. So if you have been using Midjourney, Delhi, you would have been seeing that you can create some amazing images. Now, how does this work? Your generative adversarial networks, or GANs, are implicit, which means that they generate data samples from the statistical distribution of the data. So they are again going to make use of two networks. One is the discriminator and the other one is the generator. So remember the inspiration from encoder decoder. Now we are making use of discriminator and generator. The discriminator tries to evaluate the output that is going to be generated by the generator with the original sample to see how close we are to that. And it will assign a value between 0 and 1. If the value is close to 0, then the generated sample is fake. And if the value is close to 1, then the generated sample is real. Now, what does the generator does? It is actually going to take a random normal distribution with respect to the work which is already there, and it's going to generate a sample that is close to the original distribution, taking inspiration from there. Now, how does the generator architecture works? It generates synthetic samples with respect to given random norm, and the discriminator is a binary classifier that is going to discriminate between whether the input sample is real or fake with respect to that proximity to 0 and 1. Now, when a fake sample, which is generated by a generator, is given to a discriminator, it will call out as a fake, but the generator wants to generate samples in a way so that discriminator makes a mistake in calling it out as a real one. So the generator is trying to fool the discriminator, and the discriminator is supposed to be wise enough to not fall for that. Now, the objective is this min-max optimization. Remember game theory for min-max? So how does min-max how does min-max works? Just to give you a recap, whoever starts first has the opportunity to choose. So the one who's going to start first is going to be the maximizer. The one who's going to start second is going to be the minimizer. And with the first move, you're setting a high level for the maximizer. And the next move that you have, you are setting the high level for the minimizer. Whosoever reaches that number first is the one who's declared as the winner. Again, in this case also, the discriminator is supposed to call out a fake. The generator is supposed to ensure that the discriminator is not able to do that. So again, this is a game which is going to be played between the two. End result, you are going to get outputs which are different from the data that is present with us. So you're going to get something which is unique, which doesn't exist anyhow. And of course, this is a work in progress. We see a lot of trial and errors. Even when we are using these applications, we see that 100% accuracy is not there. So this algorithm is still learning and improving as we go by. Now, it has a good number of variants. So one important variation that we have is the cycle GAN. It is one of the most popular GAN architectures which is there, and it can as an example, this kind of formulation can learn from a map between artistic and realistic images, transformation between images of a horse into a zebra, transformation between a winter image and a summer image. And we'll take the horse and zebra example in a little bit more detail. Phase app is one of the most popular examples of cycle GAN, where faces are transformed into different age groups. So the goal is to learn a mapping function, G, that stands for your generator, wherein X is to Y, such that the images that are generated by your generator are indistinguishable from the image of the Y. And the objective is used using the adversarial laws. So this is the training procedure for the cycle GAN, in which we are ensuring we are keeping in mind 3 individual losses as part of the optimization. So this is the example that we have. So wherein we are converting a zebras into a horse, a summer picture into a winter one, and a monet into a photograph, a painting that was done by the painter, monet into a photograph. And this is how the translation is working. And finally, we are able to convert, for example, this photograph into, let's say, if it's a painting painted by Monet or Van Gogh or Cezanne or Yuki Hoyo. This is a code that we have in which we are trying to make use of the generator that translates my X into Y, and the other generator that we are calling it as F that translates my Y back into X. So if this was the input image that we had of an horse, this is the predicted image wherein the horse is getting a stripes that resembles that of a zebra. There's a very good research paper on this. I'll share this with you. Please go through it. And in case you want to go for this code that I was showing, this is present in this link as well. I'll share the same. Please go through the coding as well. The second important variant of GAN is the style GAN. So do you know something interesting about these two pictures? These are not real people. These images are generated by your GAN. These people don't exist in reality. But if I had not told you that, you would have assumed that they might be my friends from foreign university or my clients in the other part of the world, right? That's not the case. These people don't exist. So style GAN is a GAN formulation which is capable of generating very high resolution images up to a resolution of 1024 by 1024 resolution as well. So what is it doing? It is trying to build a stack of layers wherein the initial layer is of low resolution images, and as you are increasing the stack, so you're starting from a 2 by 2 and then you're moving into 1024 by 1024 resolution, and as and how you're increasing the resolution with respect to every layer, you are generating a very high resolution images which look very, very real. So this is the architecture. I'm not getting into detail. I'll share the reference paper with you. Please go through it, and of course the link for code also is there. Some of the advantages of GANs is that we are able to generate a lot of synthetic data, which is primarily very, very useful if I'm going for research. My major problem, and I've seen that as a major problem for a lot of the people who are doing research, is finding the data, because usually we have a seed amount of data to work with, not knowing where to find more. So GANs are helping us out over there. Then we are getting some high quality results using them. One great thing is that we are able to actually work on data which is not labeled. So it's making the life of researchers easy by venturing into those unknown territories where we didn't know what those numbers meant. GAN is able to help us out with that. But again, with every set of advantages, primarily you are going to have a set of disadvantages as well. Number one, it's difficult to train. Number two, cost is high. Number three, overfitting. Number four, bias and fairness. And number five, interpretability and accountability. That is a big question, right? We have seen a lot of examples, a lot of news wherein we question the bias and fairness and the interpretability and accountability. Well, if you have seen that ad of 5-star, if not, please Google it and see. That also tells a lot. Okay, so the next one that we have is autoencoders. So again, we are coming back to the encoder-decoder definition. This autoencoder are a class of neural networks that are primarily used for your problem statements catering to unsupervised learning tasks. It is going to make use of the encoder and decoder. And how? What it is going to do, that the shape of the input that you're going to be working with, so that the shape of the input is actually similar to that of your output. And that happens because of the information bottleneck which is there. I'll explain that in a minute. So what happens is that the number of neurons in this bottleneck region is actually much smaller as compared to both the encoder and decoder. So this actually forces the network to reduce the information such that whatever noise is there in your input, that is reduced, and they can actually continue with the somewhat approximation of the original data rather than copying it end to end. So what we have done here is that we have designed a neural network such that it imposes a bottleneck between the networks, which forces primarily a compressed knowledge representation of the original input. Now, if the input features were each independent of one another, this compression and the subsequent reconstruction of this is going to be very difficult. However, if some sort of a structure actually exists in this data, that is, there is some sort of a correlation between input features. Remember, we were talking about the fact that we are using this methodology in order to tackle unsupervised learning, which means that we are trying to find that there is some correlation between all those numbers. So if there is some sort of a structure that exists in this data, this structure can be learned and it can actually help us to leverage when we are forcing the input through the network. So that's the icing on the cake. So this is your architecture of the autoencoders that we have, your typical input layer and the output layer, and we have introduced a hidden layer here which has this bottleneck. Now the algorithm that we are using here is to reduce the bottleneck in an attempt to learn the representation or the patterns from the given set of the data and to create a new set of data from the input. Now, what is the mathematics behind this? So a generic way to define an autoencoder using a mathematical notation is fx is equal to h. Now, your x is the input data and h is the latent variable in the information bottleneck. This formula actually denotes the encoder part of the network. The decoder will take the latent variable from the information bottleneck and then it will map them into some output, and that can actually be denoted as gh is equal to x dash. So this is going to be the mirror opposite of the encoder. Now this information bottleneck that is part of your autoencoder was introduced in 1999 actually, with the hypothesis that it can extract vital information by compressing the amount of information that can traverse through the network. So the latent variables are primarily your random variables that can be, that cannot be observed directly, but are extracted from the distribution. Now these variables are very fundamental and they actually give us abstract knowledge of the topology and the distribution of the data. The latent variables, in this above equation that we have is the one that is represented by H. They can actually differ based on the which type of variant you are using of the autoencoder. The whole autoencoder can actually be described by this function where the f and he or g are both nonlinear functions. This is the diagrammatic representation. Now, one important variant of your autoencoder is the denoising autoencoder. So we pass input that has noise added to it. And the goal here is to train an autoencoder to remove those noise and yield the output that is noise free. So I have a perfectly fine image with me. I've introduced noise to it. And then I'm asking my autoencoder to reproduce that original image minus the noise. If it is able to do that, And we are able to do that. It means we are created an autoencoder that is capable of generating new images. So this is the image that we have. This is the noise that has been added into it. You are feeding it into this autoencoder, and then the output that you're supposed to be getting is the one which is same as the input that you had originally given. Again, it has the same formula that we were talking of. Instead of minimizing the traditional criteria, the denoising autoencoder is to train to learn the noise which was there, and not to simply memorize and copy the input to the output. It also has its sets of pros and cons. Your denoising autoencoders is good for learning the latent representation in corrupted data while creating a robust representation. The cons is that in order to train a denoising autoencoder, it is important to perform preliminary static mapping to corrupt the data and then use it as an input. The second variant that we have, and the one which is very popular, is your variational autoencoder, popularly known as VAE. So it has a different mathematical construct as compared to the basic architecture that we have. And one of the biggest changes that we observe is the way latent variables are calculated. So the VA actually makes use of probabilistic approach in order to find the latent variables. And therefore, the mathematical construct is very different as compared to what we have previously seen. Now, the information bottleneck of VA consists of two components. One component represents the mean of the input distribution, and the second one represents the standard deviation. So the mean controls where the encoding of the input should be centered, while the standard deviation controls the area, which means that how much from the mean the encoding can actually vary. And you make use of the Gaussian distribution in order to the latent bit space in order to calculate the VAE. So this is the architecture of the algorithm. The encoder of the VA, also known as the approximate inference network, can be described by the given formula, and for your decoder, the formula is P model X with respect to Z. The first part of the equation that we have here describes the reconstruction likelihood, which tries to maximize the reconstruction, and the second is the regularization term. The pros and cons, VA gives us the control over how we would like to model the distribution of latent variable, whereas the cons is that the generated image is blurry because of the fact that we have injected it with the Gaussian distribution. Okay, so with that we move on to the next one, which is the graph neural networks. So the next four are comparatively newer and upcoming variants of neural networks that we have. So the first one is a graph. And what exactly is a graph? We all know, if I have to define it in terms of a data structure, it is a data structure that contains basically nodes and edges. Your node can be, if I'm talking in terms of the applications of neural network, your node can be a person, it can be a place, it can be a thing. And the edge actually defines the relationship between these nodes, right? So this particular graph tells a story of three people who met in college and how these three people know a lot of other people as well. So they all have their own networks, and some people from their network might be knowing some people from the other's network as well. So you can see the complexity that this graph portrays. Now, do you think we have a neural network that can handle this sort of a complexity? So this is where we were prompted to create a new algorithm known as the graph neural network. So these are special type of neural networks that are capable of working with a graph data structure. They are again hugely making use of CNNs. Along with that, they're also making use of graph embedding. So we are using this in order to classify images. We are using it for text classification as well. Again, because of the fact that, one word can take inference or can be used in a lot of different contexts. So when I was working on my research work, there were a lot of words in different languages that had more than 10 to 12 meanings. So how the system is capable of understanding that, in what context you are talking. So this is where the graph neural networks are going to be quite handy. Next, we have the spiking neural networks. So this is again a type of neural network that has come into picture, and this is hugely inspired by our own neurons, which our brain is full of. The pulse or the spikes that is generated in the form of electric pulses with respect to anything that triggers our brain into any activity. So the spiking is deriving the name from there, and it is used to we are making use of it where we have a lot of continuous values which we are getting in the form of inputs. So it's primarily for the applications that are on real time, wherein you have a lot of inputs that are coming your way, and you are in that real time you're trying to capture that as. So we are using it for neuromorphic computing, wherein it is being used in hardware like Intel's Lohi and IBM's True North. Then we are making use of it in dynamic vision systems, wherein your cameras can keep track of all the movements, which is in real time basis, and capturing what all those the images that it's capturing, what all they mean. And then we are also using it as a brain machine interface, that is to leverage the prosthetics and neural signal decoding. So basically to help the people who with special needs. It does have its own set of challenges as well. First of all, it requires highly sophisticated algorithms that are capable of understanding this input that is coming in such regular intervals. And because of that, the problem is that as of now, the tools or the frameworks that we have, they are more attuned to the traditional deep learning models as compared to what this type of input requires them to be. So a lot of research work is going on in this area. Next that we have is the capsule networks. So capsule networks or CapNets, they were actually introduced by Jeffrey Hinton in 2017, and they are trying to overcome the limitations of your convolution neural networks by trying to understand the spatial relationships and the object relations. So, the fact that every 3D image that we have around us, when converted into a film, converts into a 2D. So how is that happening? And when we are talking about the fact that, we have to make self-driving cars, and the fact that we are going to make devices that are capable of interacting and in terms of augmented reality. So this is going to come into play. So the capsule networks, they are going to capture the hierarchies or in the data by grouping them together in form of capsules, and each capsule is going to encode features like orientation, scale, spatial relationship by ensuring that they preserve the pose and the position of the objects. So if you, I'm hoping that we all, most of us present here are engineers, and if so, if you remember your first year of engineering, wherein you might have studied a subject which was engineering graphics, right? So I hope you remember the top view, the front view, the side view. We need to capture all that sides when we are trying to reconstruct a 3D model, right? So the capsule networks are working in that direction to capture as many aspects of the object in order to create as realistic 3D model as possible. So we are making use of it in image and object recognition, that's for sure. But then, of course, we have limitations in terms of the limited tooling and the large-scale implementations. But imagine if all this is being done, and we already know life won't be the way it is now. And the last one, deep reinforcement learning networks. Thank you so much for staying with me till this slide. Okay, so the last one. Now, reinforcement learning in itself is such a fantastic topic, right? The fact that we have realized that we needed a separate set of algorithms other than the supervised and unsupervised that we were dealing with, because situation is dynamic in real life. We cannot, like I'm sitting, anything can happen, right? I don't have a power backup, so electricity can go, and then I have to find something in order to uh, uh, make sure that we still stay connected. So keeping those in mind, reinforcement learning came into the picture, and we I'm sure most of us know how reinforcement learning algorithms implement. You have an actor, you have a reward associated to every action that they do. It can be a positive or a negative reward depending on what the action was. Now with that, we are combining deep learning in order to handle high dimensional input spaces like images or text. So it is going to make use of your deep Q networks. It is going to make use of the actor critic model, and it is going to make use of the proximal policy optimization in order to create a framework that captures the essence of having huge number of different inputs in a real-time scenario. So we will be seeing this in terms of robotics. Imagine the amount, the revolution it's going to bring in the game industry. And of course, of the fact that we are moving in a fast direction towards the autonomous system with respect to self-driving cars and industrial automation. It does have its own set of challenges. So as a it requires large amount of interaction with the environment in order to ensure that we make the real world application very much resource incentive. Then of course there's a thin line between exploration and exploitation. So we have to be mindful of that. And the increasing interest in multi-agent systems and the hierarchical reinforcement learning is going to solve complex multi-step tasks in the future, for sure. These are my list of references, and with this we come to the end of the session. Thank you so much for staying with me patiently till this hour. We are open to questions now.
Thank you, ma'am. So, anyone have any question? Kindly write in the chat box or raise your hand. Yes, anyone have any question? Okay, there is one question in the chat box.
I cannot see if you could read out for me.
Yeah, ma'am. I am reading. Just a minute. How many convolution and max pool combination is used?
It depends on the application. There is no fixed number. You can have one or you can have more depending on the number of inputs and the type of model that you're using. Not model, type of application.
Okay. The second question is that if we have the 3 convolution layers, then how many inputs we have to use?
How many inputs we have to use for the
Hmm. If we have the 3 or more convolution layers, then how many inputs we have to use? And what is the basic working of the pooling layer?
Okay. So the I'm going to repeat these answer that I had given for the earlier one. The number of your convolution layers depends on the type of application and the inputs you have, right? And how you are able to ensure that you are covering the entire input metrics that you have. So usually in convolution networks, it's more of an image that we are working with as compared to text. And the image is going to be a three-dimensional matrix that we are going to be working with. The pooling is going to be a smaller matrix that's going to cover the entire input and it's going to so let's just assume that you have a large window and then you have a smaller napkin and you're using that napkin in order to wipe the entire surface of the mirror, right? Just imagine that you have a windshield and you're trying to clean that windshield. So what are you going to do? You're going to start from one corner and then you're going to move to the next corner. Then you're going to slide your hand down so that you reach the next part. This is how. So this is exactly what the pooling is going to do for the input that you have given. I hope that answers.
Okay, ma'am. Ma'am, one more question is that can you explain when we have the RNN network, so why we go for the LSTM?
So in your RNN, we have why are we going for LSTM if we have RNN? It's a variant of your RNNs that we are using, right? So the reason that we have been using or we are using this is to ensure that if there is any information, okay, let me take the example. The fact that if we are having a conversation, right, you and I are having a conversation, right, at this point of time. Now, when you are asking this question to me, I have to go back and recollect to something which I said almost an hour back. I have to ensure that it is somewhere captured in my memory for me to go back to that part and then try to connect that and then give you an answer. If I didn't have that particular slot in my memory and it would have just evaporated, I would not have been able to answer you. So that's exactly what the LSTM is doing, which RNN was not capable of doing. So this is an additional feature that has been added into it. I hope that answers.
Okay. Thank you, ma'am. Thank you so much, ma'am. Your section is totally well explained and very informative session, ma'am.
Thank
So,
you so much.
Miss Millie, please continue.
Okay, thank you, ma'am, for delivering such an enlightening session. Your expertise made the experience incredibly engaging and insightful, providing us with valuable knowledge and inspiration to explore further. Thank you, ma'am. Thank you so much. Good to all the participants. And we will, just a minute. Thank you, ma'am.
Thank you so much for inviting me, and thank you so much to the lovely audience who stayed with me till 9. And thank the organizing team.
Thank you.
Thank you, ma'am.
Thank you, all the participants. We will share the tomorrow session link on the WhatsApp group, and attendance link only be shared in the chat box at the runtime only. We will meet tomorrow for other interesting sessions. Good night, all of you. Thank you. Thank you so much. Thank you, Nitin sir, and thank you, Shivani ma'am.
Thank you, ma'am.